Hello, I am Dr. Miller. I'm going to share with you something new that I learned in math by just asking a few questions. So let's begin. I started getting curious about how to solve high order polynomials. And one of the things that began to bother me was the complex roots. I couldn't see them. Where were they? I could see the real roots. And so starting off with that, I started on my adventures to soon discover the fourth dimension. So let's see how this happened. First, let's start off with how we get a graph. We start off with a graph by taking a function where we put in a value for x and we get a value for y. And we get a table like this. But then we discover that if we create an orthogonal set of lines and give an axis to x and y, that we can see a picture of this graph. We get to realize that the more points we plot, the more dense this will become, and it will look like a continuous curve. In this case, one of the things we notice, the graph crosses twice. And we're told that if it's a second order polynomial, that's what we should expect. Well, suppose you put complex numbers in. Well, if we start with a complex x-axis and a real axis and put in these complex numbers, minus 2 plus 2i, or 0 plus 1i, etc., or minus 1i, we begin to see these complex numbers come out for y. And one of the things we notice is when I is 0 in this set, we get the curve that we saw before. However, we notice this curve intersects in two places. It intersects in the imaginary axis at 1 plus 2i and 1 minus I. Now, if I plotted this curve, I would not see any crossings like I did with the other curve. So this curve would have been moved up and there would have been no crossings. But yes, to tell me that there were some crossings at 1 plus I and 1 minus I. Now, to look at this in another way, let's separate out those two axes. And here's the same thing again. The zeros in the real axis or in the imaginary axis sort of shine right over here. And they shine over here for an imaginary y. So we put these complex numbers in, and we get one set for y and another set for yi. Well, after a while, I started thinking, what are these things? I realized from my graph plotting experience, plotting three-dimensional plots and so on, these were different dimensions. I now had 4 dimensions by just introducing complex numbers. Now, what's the consequence of this? I'll do a little fantasizing. This allows us to interpret the complex number as a vector. We are familiar with the three-dimensional space dimensions. We now see 6. I have not yet figured out what this does to the dimension of time. Perhaps there's a way to go faster than the speed of light. On the series Star Trek, they do reference warp speed faster than the speed of light. Antimatter was theorized by Paul Dirac through the use of imaginary numbers. So maybe I'm onto something that never understood before. Okay, now if we took a look at this graph here, this would have plotted a lot of points, and we can see a smoothness in the curves of the graph. But we notice for this particular graph, it crosses over 3 pieces. This piece over here, this piece over here, and this one over here. And as we were to plot these points, how would we know where to go? Up there, down there, back there, or maybe back that way? Well, if we take into account the tangent, the slope of the curve, we'd find this was the only one that had the same slope coming out as this one coming in. And so now we could draw this as a continuous plot. And this was just merely interpretation, which gives us a little bit of satisfaction. We like the things be orderly. Now, I went to a seventh order equation. And I plotted it. And all I saw was three roots. Maybe they were out there somewhere, but I guarantee I've looked around and they're not out there. Where are they? So I look at this in another way. Now, this may sort of be confusing, but this is called a contour plot. It's a way of looking at a plot with a third dimension there. And the colors represent height, or the value of y. This one's for real eyes. This one's for imaginary eyes. And you can see by the color scheme that if the number is off here on the side with a bright color like a white or red color, which we see down here, that means we're dealing with a big area. We're dealing over here with these tones here. We see we're beginning to deal with lower areas around 0. And down here, we go to areas to -4. So we can see the darker blue colors and the brighter red colors. If you look closely, you can see some dots. There's three there. There's another 2 over here, which gives us 5. And 1 up here, 1 down here. So if we look, those 4 corners, these 3 over here, those are 7 crossings. Where are they coming from? Okay, and what we may notice where the zeros are, these dots are right near where those 0 boundaries are. But let's take a look at this in another way. You'll notice I've taken a slice across this, which gives me a plane out of this 3-dimension thing. And when I look at this plane, I'm going to plot this curve and this curve, the y and y simultaneously. The blue curve, which was the real y, crosses over 1, 2, 3, 4, 5 times. The imaginary curve crosses over 1, 2, 3, 4, 5 times also. But they only cross simultaneously 3 times, right there. So these are points or where the curves cross simultaneously at the 0 point. And that when y was 0, that's where those roots came from. These over here was a real root, and these over here were complex roots. Now, there were other planes we could go through to see that the same thing would happen. But this particular curve helped me understand what was going on. You see lots of zeros in there, but there's only 7 roots, a condition that has to be satisfied. Now, I've looked at some of the plotting packages like Demos and Maths. It's fun. And some of this stuff they can't handle because they can't handle imaginary numbers. I even called them once to show them that I had plotted a curve with my plotting package that their plotting package wouldn't plot. And I had done different tests to show how it was and found out where theirs wouldn't plot when you had imaginary numbers with just a 0 as an imaginary number. I also talked to Wolfram, and Wolfram gave a suggestion how to get around that problem with their plotting package. Boy, I felt good. I was able to do something that others were challenged by. Okay, so let's just simplify this so we can understand this better. What we have over here is the plot of a parabola. There's that parabola. No crossings. Over here, we went a little bit off of the points. And the reason why we did this is because in this particular plane that we would go through where the roots are, you can see here and here. So it would be easy to draw that plane through there. And notice that this seems to break in here. And what we find is that we use finer plotting. This green and brown areas would come together at a point, and you could then actually have a line going straight through. So this was the limitations of the graph plotting package. So if we had drawn right through here, this line would go going through here, and we see 2 intersections. There's where the 2 roots, they're in another dimension. Well, If I had trouble reading this, maybe you're better than I, but I just had a 3D printer. So I printed up a model of this and I could see this better. What's happening over here is the curve is going down, which we see in here. Over here, the curve is going up, which we see over on here. If we look at this, this almost looks like it's been rotated 90 degrees. That now this, or maybe another degree, but it's been rotated. And we notice that this low point is, instead of there, is over here now. And this high point is down here. So we can see that we've got somehow a rotated package. Okay, and the curves may look pretty much the same, a different orientation and might not quite as high. Why was I able to do this? Because I could program. I could write my own plotting package. So it's enough to have the tools that we learn in school and it worked. But sometimes they're missing. And this tool helped me get a little bit more insight into the problem. Thank you very much. Hope you enjoyed this and learned as much as I did from it. See you later. Bye.